So what if the fundamental mathematical equations that we use to describe the entire universe are actually distorting it?
Right, like completely warping reality.
Yeah. What if we've literally been staring at a warped reflection of the world for, I don't know, over a century, building our entire understanding of physics on a mathematical illusion?
It's a huge question.
It is. Welcome to today's deep dive. It is Sunday, April 5th, 2026, and we are unpacking a really fascinating, highly detailed manuscript from an independent physics blogger today.
And this manuscript is, well, it's dense, but it's incredible.
Extremely dense. But the mission today is to explore this radical reframing of how light and electromagnetic fields actually operate. And in the process, we're going to challenge the absolute bedrock coordinates used by giants of theoretical physics. I mean, we're talking Hendrik Lorentz, Albert Einstein, the big names.
Yeah, we are essentially pulling up the floorboards of modern science to look at the wiring underneath. Because when you question the very coordinate systems that physicists use to plot reality, you are questioning the foundational language of space and time itself.
Exactly. So to give you, the listener, a conceptual framework for this, because it gets weird fast downs, I want you to imagine you're playing a massive online multiplayer video game.
Oh, I like this analogy.
Right. So in this game, there is a master server. That server holds the true, unvarnished, absolute state-of-the-game world. It knows the exact position of every single object. It calculates the real physics of the environment. But then there are the individual players' screens.
Local clients.
Yes, your local computer monitor.
Yeah.
Which is just rendering a localized description, basically a model of that world.
And anyone who has played a fast-paced online game knows that the action rendered on your monitor is not always identical to the server's reality. I mean, there is lag, there's processing time.
Ping.
Yeah, exactly. Ping. The information takes a moment to travel from the server to you.
So you shoot in a target on your screen, but the server calculates that the target actually moved, like a fraction of a second ago. Your screen is just a localized, delayed description. And the core theme of our sources today is that in the world of physics, scientists might be staring at a lagging, distorted player screen while completely ignoring the actual game server.
Which is a bold claim.
Very bold. The manuscript argues there is a true, fundamental electromagnetic field operating in the server. But the mathematical spaces we use to describe it, specifically Cartesian coordinates and complex space, are just our screens.
They're just the UI.
Yeah, and because they are merely descriptions, the raw information gets inherently deformed the very moment we translate it onto those screens.
Right. And according to the manuscript, if we want to understand this deformation, we first have to really define what the server actually is.
Okay, let's unpack that.
So the true physical electromagnetic field is proposed to exist not in a flat, infinite 3D box, but as a curved, two-dimensional spherical surface.
Wait, hold on. You're telling me the universe's fundamental field isn't existing in a 3D box? Because when I picture a physics classroom, I don't see a globe. I see an X, Y, and Z axis drawn on a flat chalkboard.
Sure, yeah.
So how on earth does the 3D universe map onto a curved 2D spherical surface?
Well, think of it like sitting in the exact center of a massive planetarium.
Okay.
The physical space of the room you're sitting in is three-dimensional, obviously. But every single piece of visual information you receive, every star, every galaxy, is projected onto the curved, two-dimensional dome surrounding you.
Oh, wow.
Your entire visual reality is mapped onto that spherical surface. And the source argues that the true electromagnetic field operates much like that dome. It's a curved relational surface where all energetic interactions actually take place.
Okay, so the true reality of the field is curved, but physicists are mapping it onto a flat grid. That sounds like a recipe for a massive data distortion.
It's the root of the entire issue. I mean, you cannot map a curved reality onto a flat descriptive surface without something breaking. If you take a literal 3D physical globe and try to flatten it onto a 2D piece of paper, you inevitably tear the paper or you stretch the continents. It has to happen.
But math just doesn't work otherwise.
Exactly. And mathematical spaces do the exact same thing to the physical information of the universe.
Which brings us perfectly to the first of our two screens, or mathematical maps, that the text focuses on. Let's look at the Cartesian trap.
Ah, yes. The classic Cartesian grid.
Right, the Cartesian coordinate system is probably the most famous map in all of physics. It's a standard grid. X is left and right, Y is up and down, Z is forward and backward.
We all learned it in middle school.
Exactly. So how exactly does this specific grid deform the information of the universe?
Well, Cartesian space assumes what we might call a God's eye view. It breaks the universe down into neat, simultaneous slices of time across vast distances.
Meaning what, exactly?
Meaning it assumes you can look at coordinate A and coordinate B at the exact same moment and know exactly what the field is doing at both locations instantly.
Instantaneously. Which, the sources compare this Cartesian grid directly to the Mercator projection of a world map.
Which is a brilliant analogy.
It really is. For you listening, the Mercator projection is that classic rectangular map you probably had on the wall in your elementary school classroom.
Right.
So why is that specific map such a good analogy for this physics problem?
So if we connect this to the bigger picture, the purpose of a Mercator projection was purely practical. It helped 16th century sailors navigate using straight lines.
Right, compass headings.
Exactly. But to keep the grid looking flat and square on the paper, the mapmaker had to drastically stretch the land masses near the poles. That is why Greenland looks the exact same size as the entire continent of Africa on a Mercator map.
Even though Africa is actually, what, about 14 times larger?
Yep, something like that. It prioritizes straight-line navigation over geographical truth.
So it's a useful map for one very specific task, but it absolutely lies to you about the actual geometry of the world.
It has to lie. And Cartesian space does the exact same thing to physics. It forces a curved electromagnetic reality into a flat 3D grid, prioritizing simple straight-line algebra.
Okay.
But in doing so, it completely mishandles the near-action time delay of light. A Cartesian grid plots the universe as if light travels instantaneously across the framework, allowing for simultaneous now moments everywhere at once.
Which is physically impossible.
Right.
To bring this to life, the source provides a really memorable example about photographing a moving truck.
I love this part.
Yeah, so imagine you take a picture of a long truck driving past you on the highway. A photograph takes a 3D object moving through time and flattens it into a 2D frozen image.
Right.
But light takes time to travel. The light bouncing off the back bumper of the truck actually takes slightly longer to reach your camera lens than the light bouncing off the front bumper.
Because it's further away. So by the time all that light hits the camera lens to form a single image, time has actually passed differently for different parts of the truck.
That is so weird to think about.
It is. You are capturing a composite of different moments in the past, squished into one single present image. And Cartesian grids struggle to natively represent this information delay.
Because they want everything to be happening at the exact same time.
Exactly. They try to freeze a moment in time across the whole grid, just like that photograph, completely ignoring that the server operates with a strict, finite speed limit for information.
Okay, so if the flat Cartesian grid lies to us about time and simultaneity, how do we fix it? Like, can we build a map based entirely on the observer's timeline instead?
Well, you can try.
Right, because our sources say there's an alternative screen, which leads us to complex space.
Yeah, complex space offers a very different perspective. Instead of that God's eye view trying to see everything instantly across the whole universe, complex space is deeply tied to the unit circle and treats the observer as the absolute center.
Okay.
It introduces a camera eye perspective. And in the context of our map analogy, the text equates complex space to an azimuthal equidistant projection.
I really love the specific visuals the author provides for this. So imagine taking a map of the entire Earth, but you center it perfectly on Tokyo. Or you draw another map perfectly centered on the island of Hawaii.
Right. In an azimuthal equidistant map, if you draw a straight line from that exact center point, say Hawaii, to any other place on Earth, the distance and the direction are perfectly accurate.
It captures the true reality of radiating outward from a single observer.
Exactly.
But the deformation is still there, isn't it? It's just hiding it a different way. The text points out that in an azimuthal map centered on Hawaii, the distances radiating directly from the center are flawless. But as you move to the outer edges of the map, the shapes of the continents become violently stretched.
Oh, yeah.
Like Antarctica stops looking like a continent at the bottom of the globe and becomes this massive, distorted ring of ice wrapping around the entire outer boundary of the map.
It's wild to look at. And that physical stretching on the map represents the severe spatial distortion required to make the time delay work in complex space.
Okay, break that down for me.
So think back to our video game analogy. Imagine looking at a 3D cube in your game environment. You are standing right next to the front corner. That front corner renders instantly on your screen, right? Zero ping.
Right.
But the far back corner of the cube, the data for that corner takes time to reach your client. It has server lag.
So in complex space, that far corner isn't actually happening now. It's happening a fraction of a second in the past because of the speed of light.
Exactly. And the text gets really specific with the math here. If you are at the center point, right, coordinate 0, 0, 0, looking at a 2 by 2 by 2 cube, the corner of that cube at coordinates 1, 1, 1 isn't happening now.
Because of the distance.
Yes. Because of the speed of light, that corner exists the square root of 3 seconds in the past. Complex space accounts for that ping beautifully. It perfectly describes the delay of light radiating inward to your specific camera eye.
But at a cost?
A huge cost. To plot that time delay accurately on its framework from a single localized point, it has to entirely warp the broader spatial geometry of the cube itself.
Just like the azimuthal map turns Antarctica into an unrecognizable ring.
Exactly. It entirely destroys the broader spatial geometry.
So neither screen is perfect. The Cartesian screen gives you a nice, neat grid with recognizable shapes, but it completely lies about time and simultaneity.
Yeah.
And then the complex screen tells the absolute truth about the time delay of light from a single point, but it violently distorts the geometric shape of the space around it. Both screens warp the raw data of the game server.
They absolutely do. And this mathematical mapping issue isn't just an abstract thought experiment, you know. It directly caused one of the most significant scientific crises in the history of physics.
Which is just crazy. Let's transition into that history, because this is where the implications get massive for the listener. Mistaking the map for the territory, confusing the lagging client screen for the actual game server, resulted in a fundamental glitch in the 20th century.
A huge glitch.
So here's where it gets really interesting. How did early physicists navigate this? Starting with Ole Romer.
So Ole Romer was a 17th century astronomer, and he successfully calculated the finite speed of light long before we had, you know, modern laser instruments or anything like that.
Which is mind-blowing on its own.
It is. He achieved this by meticulously observing the eclipses of Jupiter's moon, Io. And crucially, his mental model didn't rely on a rigid Cartesian grid centered on Earth. Romer treated the electromagnetic field as a real stationary background.
So he treated the field as the true server, and the planets were just objects moving through it.
Exactly. He realized that while the Earth is orbiting the Sun, it is sometimes moving toward Jupiter and sometimes moving away from Jupiter.
Right.
So when moving toward Jupiter, Earth is basically driving into a headwind of the light coming from Io's eclipses. When moving away, Earth is running with a tailwind, so the light takes longer to catch up to us.
Oh, that makes perfect sense.
Right. By measuring the time differences of those eclipses, Romer proved light had a finite speed relative to that stationary background field.
He was interacting with the actual physics of the server, and the math worked perfectly. But then, and this is where it all falls apart a couple of centuries later, the physics community ran into a brick wall with the famous Michelson interferometer experiment.
Ah, yes, the Michelson-Morley experiment. This was designed to measure the speed of the Earth moving through that exact stationary background field, what they often called the ether at the time.
Right.
So they built a device that split a beam of light, sent it in 2 perpendicular directions down long arms, bounced the beams off mirrors, and brought them back together to see if they interfered with each other.
Let's visualize that setup for the listener, because the sources are very specific here. The center of this device is sitting on Earth, which is hurtling through space. So the device itself is sliding through the server, right? Like at time -10, it is at position -6. At time 0, it is at position 0. At time 10, it is at position 6.
Correct.
So the physicists expected this movement to create an effect similar to a swimmer in a river.
The river analogy is perfect. If you have 2 swimmers of equal speed, and one swims directly upstream and back down, while the other swims straight across the river and back, the cross-river swimmer will always return first.
Because the upstream swimmer loses more time fighting the current than they gain riding it back.
Exactly. The physicists assumed light bouncing along the arm, pointing in the direction of Earth's motion, would be fighting an ether headwind and take slightly longer to return than the light bouncing along the perpendicular arm.
But the experiment famously produced a null result. The light beams returned at the exact same time. There were no interference fringes at all.
Nothing.
It was a complete shock.
A profound shock because it seemingly broke the rules of physics as they knew them. So this raises the critical question: how did the physics community react to this null result? Physicists like Lorentz looked at this impossible outcome. And here's the crucial insight of our source material. Lorentz was looking at the result through the distorted Mercator map of Cartesian coordinates.
Oh, he was looking to his lagging player screen, not the actual server.
Precisely. His flat Cartesian map assumed space was a rigid grid and time was universally simultaneous. On a rigid grid, if a device is moving, light simply must take longer to go back and forth along the axis of motion.
Right. There's no way around it geometrically.
The flat map couldn't easily explain how the light returned perfectly simultaneously without breaking its own internal algebraic rules. So, to make the math of the flat Cartesian map match the physical result of the experiment, Lorentz was forced into a corner. He had to introduce a radical new concept.
Okay, wait. If the light speed couldn't change and the grid couldn't bend, he assumed the physical measuring apparatus itself must be shrinking.
Yes. He deduced that the physical arm of the interferometer moving in the direction of travel must physically contract in length by the exact mathematical amount needed to make the light beams arrive at the same time.
Wow.
This became known as Lorentz contraction.
So synthesizing the text's ultimate claim here, Lorentz contraction wasn't actually a physical reality at all. It wasn't a property of the universe. It was a math patch.
A math patch is the exact right way to conceptualize it.
It was literally a software update. The developers of the physics model saw a glitch on their distorted 2D Cartesian screen where the light was behaving weirdly. But instead of realizing the underlying map projection was flawed, they wrote a patch Lorentz contraction to force the objects on the screen to shrink.
Yeah.
They did this simply to make their local screen math match the results of a true, curved 3D electromagnetic server.
The author is pointing out a profound paradigm shift here. If Lorentz had stepped back and realized he was trying to plot a curved relational reality onto a flat God's eye map, he wouldn't have needed to invent physical space contraction.
Because the curvature handles it naturally.
Right. The natural geometry of a curved spherical surface inherently accounts for the light's behavior without needing solid metal arms to magically compress. The tragedy of modern physics, according to this manuscript, is that they confuse the mathematical deformation of their chosen map for a physical deformation of the actual universe.
And Einstein just inherited this math patch.
He formalized it. Einstein elevated Lorentz's math into the physical theory of special relativity, and later Minkowski baked it into the concept of spacetime. But the underlying reliance on those flat coordinate assumptions remained embedded in the foundation.
So what does this all mean for you, the listener? Why does an esoteric debate about 20th century physics coordinates matter to your life right now?
It's a fair question.
It matters because it is the ultimate lesson in the invisible limitations of the frameworks we rely on every single day. Whether you are prepping for a boardroom meeting, analyzing a massive spreadsheet of consumer data, or looking at a map of the world, you have to remember that your tools are just descriptions.
Yes, every single analytical framework deforms raw information to make it digestible.
A spreadsheet flattens the chaotic human reality of a business into neat rows and columns. A Mercator map distorts the size of continents to keep shipping lanes straight. You have to constantly ask yourself, what is the true reality of the situation? And what is just the lag or the stretching on my local screen? Do not confuse the localized rendered image for the actual game server.
This deep dive fundamentally serves as a masterclass in critical thinking. When someone presents you with an absolute, immutable fact, it is crucial to ask, what kind of map projection did they use to arrive at that fact?
Exactly.
Are they looking from a detached, simultaneous grid? Are they looking from an isolated center point perspective? The assumptions built into the tool will always color to the reality of the result. If we forget the limitations of the tool, we risk inventing our own math patches to explain away inconsistencies in our lives, rather than recognizing we're just using the wrong map.
Which brings us to a final lingering thought for you to take away today. Let's look at the cutting edge of science. If Lorentz contraction and the fundamental coordinate systems of special relativity were just math patches applied to a distorted Cartesian screen, what else is built on top of that shaky foundation?
Oh, I mean the entire bedrock of modern theoretical physics.
Right. The foundational equations of quantum mechanics today are heavily reliant on these exact same inherited Cartesian coordinate systems. So what hidden math patches are scientists currently accepting as physical reality right now?
It's spooky to think about.
What strange mind-bending paradoxes of quantum entanglement or dark matter or wave-particle duality might simply instantly disappear if we finally updated our mathematical map to match the true spherical physics engine of the universe? Are we trying to decode the mysteries of the cosmos, or are we just trying to debug a lagging client screen? Keep questioning the maps you are handed, no matter how beautifully they are drawn. Thank you for joining us on this deep dive. We'll catch you next time.